Hello, everybody, and welcome to this talk. My name is Niklas Rach, and I'm currently a PhD student at the Dialogue Systems group at Ulm University. In the following, I would like to introduce our work from argument search to argumentative dialogue, a topic-independent approach to argument acquisition for dialogue systems, which we did in cooperation with the Ubiquitous Knowledge Processing Lab at the Technische Universität Darmstadt. Now, before we get into the details and the specifics, I would like to give a brief overview and motivation for the work. So the scenario that we are looking at, or the general setup, so to say, are dialogue systems with the capacity to argue. An example of such a system would be our persuasive dialogue system EVA that we published a couple of years ago, and it's shown here. So it includes a virtual avatar that interacts with the user and also the user interface. Now, the goal that we pursuing here in this work is to enable such systems to discuss multiple different issues or topics. So in general, to enable topic flexibility. The problem that we are facing along the way is that many argumentative systems rely on structured knowledge about arguments and their relations, so-called argument structures. An example of such a structure is shown here, including the different arguments and their individual relations towards each other. The problem with this dependency is that the generation of argument structures is frequently time-consuming and inflexible. It's done, for example, through annotation or crowdsourcing experiments. Our objective now is to retrieve argument structures that meet the requirements of the corresponding systems automatically. We do that by utilizing argument search engines, which recently evolved as an application from the field of argument mining. An argument search engine retrieves a pool of pro and con arguments for a given topic from various web sources and can frequently be accessed by API, which is important for their combination with dialogue systems. Still, the search results do not include information about the relations between the individual arguments. So the argument search engine that we are using here in this work is Argumentative, and here you can see a picture of the corresponding web interface, including the search query or topic nuclear energy, and then the list of pro and con arguments that are retrieved for this search query. So given the search results, we then propose a mapping of the pool of pro and con arguments that are retrieved by the search engine into an argument structure as depicted here on the right-hand side. So at the top, we have the pool of pro and con arguments, and at the bottom, we have the target structure that the arguments are mapped into. To achieve this mapping, we estimate possible relations between the arguments and then derive the final argument structure from these estimation results. The target structure that we are considering herein is a directed tree with the topic as a root. And we also assume that each argument has one unique relation towards another one, but can be targeted by multiple others with a relation, as also shown in the picture on the right. So to estimate possible relations between the arguments, we train a classifier to predict the labels relation or no relation from argument pairs on a relation classification corpus, and the polarity of the relation is then derived from the stance that is provided by the search engine. The classifiers that we are considering are, first of all, a fine-tuned BERT model, and second, a support vector machine that is trained on BERT sentence embeddings. The results on the corpus are as follows. So BERT achieved an accuracy of 80% in a 5-fold cross-validation, and the support vector machine a accuracy of 77.4%. For the actual task, so the classification of search results, we consider two different configurations. First of all, we predict relations between all argument pairs in the search results, and in the second configuration, we use the clustering API of Argumentative to cluster the arguments thematically and then only estimate relations between arguments within a cluster. Given a successful relation classification, the tree generation then works as follows. So first of all, we derive probabilities for each relation from the classifier confidence, and then use one of the following two methods to derive the final tree structure. The first method is binary integer linear programming as proposed in this work. And the idea is to optimize the sum of probabilities for relation in the tree under structural constraints. So basically treat the tree generation as an optimization problem. The second method is called traversed and modifying graphs. And here we first take the most likely relation for each argument to another, and then look at the substructures or the subgraphs that result from these relations. If there is a circle in such a subgraph, we redirect the relation of the argument that has the most probable relation to an argument outside of the subgraph to break the circle. So the complete pipeline then is shown here. First of all, we have the topic on the left-hand side, which is given to the argument search engine, which retrieves a pool of arguments, which can then either be directly given to the relation classification or clustered and then given to the relation classification. Either way, the relation classification outputs a probability matrix, which is then used by the tree generation to derive an argument structure, which can then in turn be used by the argumentative dialog system. For an evaluation, we first of all conducted a preliminary annotation study where we investigated the different combination of methods that we are using herein, and found that BERT plus traversing and modifying graph works best in terms of performance and computational time. So we achieved slightly better results with BERT and binary integer linear programming, but the underlying optimization problem renders this method unsuitable or inflexible regarding the amount of arguments. And so we decided to use BERT and TMG for the final evaluation. To this end, we generated artificial dialogues between two virtual agents with the retrieved argument structures. And the interaction between the two virtual agents is modeled as a dialogue game for argumentation. The evaluation is then done in a crowdsourcing experiment where the resulting dialogues are assessed utterance-wise with respect to their coherence. To rate the utterances, the participants answered the following three questions. First of all, do you understand what the speaker wants to say? Second, does the utterance address its reference? And third, does the utterance contradict the speaker's position? And if the utterance is comprehensible, does address its reference, and does not contradict the speaker's position, we say that it is fully coherent. The specific setup for the evaluation is discussed next. So we retrieved arguments for 7 different topics, namely nuclear energy, abortion, self-driving cars, school uniforms, death penalty, animal testing, and marriage. And for each of these topics, we generated 2 structures, one with and one without clustering. And the results that are achieved with the structures on the topic marriage are then compared with the results achieved with an annotated structure that we proposed in an earlier work. We generated 2 dialogues per structure, which resulted in 30 artificial dialogues divided into 10 groups with 3 dialogues in each group. We considered 7 raters per group and derived the final score from the majority ratings of the best agreeing 3 raters. Now let's have a look at the numbers next. So first of all, we compared the 2 groups with and without clustering on all topics for which we don't have an annotated structure available, which are nuclear energy, abortion, self-driving cars, school uniforms, death penalty, and animal testing. And the explicit numbers are shown here. So the upper half of the table contains the results without clustering, the lower half contains the results with clustering, and the individual numbers are the ratio of positive ratings and overall ratings included for all three evaluation questions: comprehensible reference, polarity, as well as the overall coherence. So the first thing that we can see here is that the results vary between the investigated topics and also the different groups or configurations, so with and without clustering. We then compared the overall results of the two groups, but found no statistically significant difference there. In the next step, we have a look at the comparison with an annotated structure for the topic marriage. Again, these are the results. The upper half of the table includes the specific results. The lower half includes the p-values of a pairwise comparison of the groups. So the first thing that we can see here is that the annotated structure clearly outperforms the automatically generated ones. In fact, the annotated structure reaches a perfect score of 1.0 for all investigated categories. This is not surprising because the structure was tailored to the specific task, but still we can also see that the pairwise comparison shows no significant difference between the annotated and the automatically generated structures without clustering for the reference category, which is of particular interest because the reference category is directly influenced by the relation classification that is the major part of this work. So in summary, we have proposed an approach to automatically retrieve argument structures for argumentative dialogue systems. And our approach allows the corresponding system to discuss any topic on which a search engine can find suitable arguments. We evaluated the approach in a crowdsourcing experiment, and our results first of all indicate that there is a dependency on the available data, which is not surprising. They also indicate the expected room for improvement in comparison with an annotated structure, but also the general feasibility of the approach. So basically that we are on the right track. Now, the task for future work is hence to improve the retrieval performance to get better structures. And an additional thing that we would also like to investigate is to retrieve weights for the arguments in the structure based on the confidence scores of the individual pipeline components. Yeah, that's everything from my side. Many thanks for your attention. If you have any questions, I would gladly answer them during the Q&A session.